Welcome. Before I start, I wanted to sample a bit what the background of the audience is, more or less, because I am not familiar with this kind of setting. So, well, are you familiar with Boltzmann machines? I hope not too much. On the other hand side, I definitely would like to talk to some experts to exchange about how they work in practice. And I don't know, can you give me some, maybe raise hands who has never heard of RBMs? All right. And who has used them in, okay, less people. And who has used them in deep architectures? All right. So we talk later on. Yes. So, pragmatic introduction to restricted Boltzmann machines. So, pragmatic is meant in quotation marks because I didn't use them in practice. I'm more or less new to the field of deep learning, but I have a background in machine learning. But I was willing to give this talk because we have an upcoming project that is probably going to deploy autoencoders, so I want to see how this works, and what you started with is survey the experience of other people. So two motivations why you would do that. On the one hand side, or why you would care about RBMs is they provide one possibility to facilitate supervised learning. So what does that mean? Deep learning fundamentally suffers from the problem that the more and more layers you have in your network, the harder it is to train them from scratch via backpropagation of error signals if you initialize the weights randomly. And another problem in real life, so if you have industrial, generally in real life, labeled data is not abundant. So what's the current solution? So you have human experts. So the nice idea of deep learning is, okay, these networks can learn the features, but now you need the experts that know about the hyperparameters and stuff. And they then hopefully come up with tricks such as inventing the ReLU instead of the sigmoid nonlinearity, which helps in avoiding the vanishing or exploding gradient problem. And two other ways to circumvent this problem slightly. First is transfer learning. This is what we currently do. So we leverage what other people have done already. So people publish their trained network weights, and then if this is available for a task that is similar to yours, you can tweak the network to your task. Or the second branch is, okay, you pre-train networks layer-wise, increasing the depth of the architecture, either unsupervised or supervised. This idea is around for quite a while. And for detailed references, please consider this Schmidt-Huber review, such that everybody is accredited in the right way. Motivation number two is generally unsupervised learning is quite interesting. And so restricted Boltzmann machines are on the one hand side building blocks for deep neural networks, and on the other hand side they are probabilistic graphical models. And this per se is interesting because they allow to learn structure of potentially high dimensional data, and so in terms of probability distributions, and then you can do full probabilistic inference. So in this talk I'm gonna introduce restricted Boltzmann machines, having these, and in the second part, so this second part of this evening will have a practical coding session, and in my second part of the talk, I'm gonna teach you the basics, so the mathematical background for what you need to know to get the coding done, and then third, I talk about how to stack RBMs on top of each other. So, without knowing too much what it is, so what a RBM is, on the left-hand side we see, do we have a pointer or so?
On the desk.
So this is an RBM. It has visible units, these nodes here, and hidden units and connections between them. And what means to learn them or to train them means you fit parameters that these guys involve. Based on using training data, for example, images of handwritten digits. And once you have learned these parameters, you can generate samples from this joint probability distribution, which means you can generate new images. That's a scenario of unsupervised learning because we don't provide any labels. Supervised learning can be, for example, as done here, formalized as such. So you have labels and you use them in order to fit your parameters, for example, by concatenating the input with here a one-hot representation of a binary vector that is of length 10 because you have 10 different digits. And if you've learned this joint distribution, you can sample from these guys or you have the input image, fix it, and sample the remaining variables, and therewith you get the probability distribution about which class this image might belong to. So the second entry here, beginning from 0, is active here. So this network has learned, okay, this is class 2. And a third way to have a view on the third facet of RBMs is that you can take the hidden layer representation as a feature representation, and then take this and train a classifier on top, or use it as input to any other system. So it's pretty flexible. So let's get a bit more concrete. So let's fill this structure with more information. This is a probabilistic graphical model, which means that the nodes are all random variables. We have weights. It's a bipartite graph, so the weights are symmetric, so information can flow up and down. And the joint distribution of these guys is given by the Gibbs distribution, which is a very general form that allows this, like the Taylor series expansion for functions. This is the a general form of describing probability distributions of Markov random fields, and RBMs are a particular instance therefrom. And Z is you need for normalization, so you sum out about all visible and hidden states. And if the energy function for a restricted Boltzmann machine that does not have connections between units of the hidden layer or the visible layer is given by this equation, so it's linear in its parameters. What are the parameters? These are the weights and the biases of visible and hidden units respectively. All right, so far to the introduction. Now let's have a look at what we're going to implement later on. So the task is to implement an RBM training. There's several algorithms out there that have been proposed. One of them is contrastive divergence, proposed by Hinton. And I follow the notation of Fisher and Eagle, which is a paper that introduces RBMs from the probabilistic point of view. You don't have to understand this in detail right now, but I will guide you through this and basically focus on mostly this line here, because this is, you might think, are you crazy or so? Actually, there's some approximations involved that I think in the end are going to determine how well RBMs really work, how good the performance of them is in practice. So, stepping a bit back, what does unsupervised learning mean? Well, you have to find the parameters of the model distribution based on sample data. So our parameters are all the weights, all the biases. And we want to model the true distribution Q, which we don't know. We just have samples therefrom. And we assume a model distribution that is parameterized by theta. And ideally, you would minimize the Kullback-Leibler divergence between these two guys, so that's a distance measure between two probability distributions. If you write this out, you find this is the entropy without depending on theta. So the only thing that is left is this guy here, and this is unfortunately not tractable because this involves summing over all possible values that X may assume. And if you think of high-dimensional data, for example, images, that's all possible images that are out there in the world, and that's not tractable. So any practical algorithm, or one way to approximate that is you approximate this expectation value with samples from with the finite samples you have, and this is the log likelihood. And so the minimization of the Kullback-Leibler divergence is approximately the maximization of, or can be approximated by maximizing likelihood. So now we know, okay, we want to maximize the likelihood. How do we do that in practice? That's not possible analytically, so we do gradient descent. And here is the log likelihood for Markov random fields with latent variables. So latent variables are in our case the hidden units. So we plug in the Gibbs distribution where we marginalize over the hidden states. And if we write that out with the partition function set, we get this form here. And if we calculate the gradient of this guy here, it has this particular structure which shows, okay, there's one first term can be interpreted as this increases the probability of training data, and the second term decreases the probability of the model data. So what does that mean? We have a certain model structure given, and whenever we update the parameters, we tweak the theoretical model distribution to the data. And this can be seen here because low energy states have high probabilities, so there's a resemblance with thermodynamics and physics. And this, so here's the energy gradient, and we move away from that in the opposite direction due to this minus sign, so this increases the probability and given conditioned on data. And here we sum over the full distribution, therefore it's the model data, and we have a plus sign, so we increase the energy and then decrease the probability. So now this here holds for Markov random fields, which is something more general than an RBM. But to make things tractable, let's focus on RBMs and how they make things way easier. So first thing that we can make use of is we have no intra-layer connections. Therefore, the probability distributions of, if we condition on either the hidden or the visible states, both of them factorize, which is very helpful. And second, if we restrict ourselves for the moment to binary units, we can compute these terms in the sums. And what we get out here is the traditional transfer function of an artificial neuron, and therefore we can interpret this as a stochastic neural network. And if you use these two things and plug that in the gradient, what we get out is this here. So that was the former equation. Now just with deriving with respect to the weights, we get out these two terms, and this is now easy to compute, whereas this is still a sum over all visible states. So we need something. So this is still very expensive, and now contrastive divergence is one way to approximate that. So instead of computing the expectation value over the entire distribution, you could imagine, okay, let's approximate this with a few samples. So let's draw samples from a distribution. And in the case of contrastive divergence, we actually just take a single sample. So we avoid the sum by just taking a single sample. And the second point is that how we generate the samples. This is based, this Markov chain Monte Carlo method. in this particular case Gibbs sampling, and so this is a way of, if you have a multivariate distribution, to generate multivariate samples by holding all variables except for one fixed, and then generate each at a time, and therewith build up the multivariate sample. And in order that such a sampling procedure matches the true distribution, you have to usually run it for a certain time until it converges to stationarity. But k-step contrastive divergence just doesn't wait that long. And in practice, we are actually going to set k to 1 because it turned out that this works pretty well. And therewith, we have our final approximation. The data part is, this is just a data sample. And this visible sample here is obtained by taking a data sample as input to the RBM, propagating it up to generate hidden states, and then propagating down again to generate a visible state, so a confabulated one. And K tells you how often you do that, so once up and once down should be sufficient for what we do. All right, so now one has a feeling what approximations undergo this equation here, and it's similar for the biases and for the biases of the visible and hidden units. The Gibbs sampling happens here, and because we have seen that the conditioning on visible and hidden states actually factorizes, therefore we can perform block Gibbs sampling, so generate all the hidden and visible states at once. And so in the next step I want to show you how you've got a lot of for loops in here, but the implementation is going to be in NumPy or SciPy and SciPy, or basically probably just NumPy. Yeah, so what is there very convenient is if you have vectorized formulation. So taking this equation here, again from the previous slide, this is all scalar. So weights are scalar and these probability values are scalar and so on and so forth. But if we introduce the matrix notation, so W actually we have weights as many as n visible by n hidden units, and then we work in batches, so we concatenate a few samples, so this is given by the batch size, so the visible data is batch size by the dimensionality, so that's the number of visible units, and the hidden matrix is batch size by n hidden ones, and therefore you can rewrite the probability, conditional probabilities as such, and get this formulation. And if you go back, you see what are all these for loops about. So for all the samples out of the batch, do this and that. This is for loop vanishes because we stack the data in the matrix V. Here we run over hidden and visible units, so that's as well what goes into a vector dimension or tensor dimension, and accordingly for these other guys. So all this vanishes and can be written quite shortly. Okay, so far, however, this was plain vanilla gradient descent. In practice, we have to do a bit more. So we have to, or we can control actually the learning rate. So how large is the gradient actually going to be? And further on, we add some L2 regularization to encourage small weights in the RBM literature. This is typically called weight decay. And can as well be motivated by big Gibbs sampling, but a more intuitive way of thinking is that you have the sigmoid nonlinearity, which is bounded between 0 and 1. and the activity, if it's too large or too low, then this is drives the network state into saturation, and you can prevent this with spending small weights. And this momentum term here is, well, for now it's a physicist say, okay, it speeds up the learning process. So far so good. So we have, I said k can be set to 1, and in total now we have collected some hyperparameters. So ideally, let's say for the last 3 of them, you either perform cross-validation or you find literature values or so. But actually a tricky one is the number of hidden units, because for your particular problem, potentially nobody can tell you, but there's general intuitions to that. So here we see for MNIST, so handwritten digits again, an example of 16 versus 100 hidden units, and what we see here is the receptive fields. On the left-hand side, if we have 16 hidden units, on the right-hand side, if we have 100 hidden units, and so the receptive fields are basically, we plot here in grayscale the weights from hidden to visible ones, and we see if we spend less hidden units, in order to capture the entire distribution, this is more abstract stuff, and you could maybe see even like entire digits here, whereas if you spend more hidden units, each and every receptive field gets sparser, and we can, by combining all these, therewith explain an image. All right, I hope this was not too confusing. So now we are able to train a single RBM. Once we have done that, it's actually pretty straightforward to stack them on top of each other, to do all sorts of things. For example, so this is what we've done so far. We have input data, and in this case 2000 hidden units, and train this guy, but we can take this feature vector as input to the next RBM, and so on and so forth, to build up a whole stack. And for example, as these connections are both symmetric, we can actually, once we have a very abstract hidden layer code, we can propagate the activity down again. So we get a decoder and entirely what is called a deep autoencoder. And this is completely trained in an unsupervised way. And then we can fine-tune all the network parameters with backdrop, with whatever cost function we want to spend on. Here, for example, the reconstruction between the original image and the so here's the reconstruction, here's the original image, and you minimize the error between them, for example. So here's shown how this works, for example, practice on three different data sets. So here we have artificially generated cubic splines, handwritten digits, and here face images. And what this paper wants to show basically is that you have here in the first line always some original samples. In the second line, the reconstruction that you achieve with the deep autoencoder. And in the next line, some different variations of PCA. And the main message is, okay, this with using a deep autoencoder, this works better. Another view on the same problem here for the digital image case is now a slightly different autoencoder and PCA in 2 dimensions. The autoencoder has the last hidden layer has only 2 dimensions, 2 units, and so this completely unsupervised, and only afterwards labeled data points are labeled in or given color by according to which class they come from, and you see, okay, PCA is more disordered, whereas the deep autoencoder gives you more structured representation. So it's a useful pre-processing. And interestingly, the same holds actually for text documents. Here, the deep autoencoder is compared against latent semantic analysis, which is something similar to PCA, and the same message is given here. One remark on this, actually it would be interesting to see here for both text or images to compare that against ICA, because PCA actually just captures the pairwise correlations, whereas RBMs are able to extract higher order correlations, and so I would expect that the reconstruction with ICA is way better actually. Now here coming back to the original motivation, so unsupervised pre-training facilitates supervised fine-tuning, originally proposed by Ballard in 1987 probably. And what we see here on this synthetic cubic splines data set, on the left-hand side a deep autoencoder, a squared reconstruction error, here a shallow one. And if the deep one is randomly initialized, you can't get the error down, whereas if you pre-train it, this works. And for the shallow one, you have this effect as well, but not as severe actually. And but in the end, the question is, this reconstruction error is around 1, whereas this is as well. This, if you look detailed, this is a bit better, but actually, in terms of performance, these two scenarios perform similarly. All right. So far to RBMs, what I was wondering about is, like, we currently work with convolutional networks. And you have these, on the RBM side, the probabilistic side, you have these nice properties that you can sample from your network and do probabilistic inference, whereas convolutional networks are usually just deterministic. Nevertheless, they are the standard for visual object recognition tasks, and actually, people nowadays manage to train incredibly deep networks. So I was wondering, are there any efforts, or what's the difference between the two, and are there any efforts to potentially combine them? So important features are that you have weight sharing within convolutional layers, and where you compute so-called feature maps from this, which in turn are then pooled in order to get higher order activations. And this pooling introduces a sort of invariance across the dimension where you do that. What we know from visual convolutional networks in visual object recognition is that actually, like, what people have spent time upon since 2012, basically when these networks won large image recognition competitions, that increasing depth actually increases performance substantially. And theoretically, we know from DBNs that the lower bound of the data log likelihood increases with each layer that we add on. So that helps, and so these resources of this talk are found here. I would have a few notes on how to implement that. The coding session is gonna be in NumPy because it has less intellectual burden, but in practice you code these things on using GPUs, and so there's tutorials for this kind of things out there. But if you want to use predefined layers, there's, for example, if you use Theano, but there's other frameworks, then you have even libraries on top of that allow you to predefine to use predefined layers and stuff, and it actually becomes very short and easy to get these things to run on GPU.
Cool. Then, I mean, are there any questions? I know if there are no. Oh, you have one.
So there are some questions. I don't know if we have time, but
is it a short question or a rather longer question?
Well, the question is short. I don't know about the answer.
Okay, I mean, let's just ask a question. It's a quick answer.
I got a bit confused between RBMs and autoencoders in one of the last slides that you showed.
Yeah.
Because I know that autoencoders are just usually trained as supervised neural networks, where you just put the input as the output and have this bottleneck of hidden units, which is usually smaller than the input and the output. But here you describe it in the context of RBM, so I'm a little bit confused.
Yeah. What I maybe did not really convey is these things are very tightly related. So you can, so it's a very similar architecture. You can, basically autoencoders have deterministic units and RBMs are stochastic, but you can, these conditional probabilities where you see this neuron activation function, you can use this and not go to sample binary states, and this is then deterministic again. It becomes kind of similar, but still there is different properties because, for example, RBMs try to model they do model the probability distribution, whereas the autoencoders, that's completely deterministic. And so autoencoders are good in reconstructing this very exact image that you show, whereas RBMs do that on average, more or less. Maybe that's not completely right, but this is more or less the... So there is more aspects to that.
I would also encourage you to, in the break, and everyone who's interested, that you can use the whiteboard and dig deeper into this. So we're now having like a short break of around 30 minutes, if I remember correctly, 30 minutes. And TNG was so kind to provide some food. And then after the session, the food session, we would go back to the computing session and get out our laptops and start just coding what Christian has introduced. And then see.
Tell us what we should install on our machines.
Oh yeah, you're right. I almost forgot it. So we've already provided some code snippets, and you can download them online. If you just go, I think, Uwe, you uploaded it to the Meetup page, right?
Yeah.
So if you just go to the Meetup page, there's a link, and you can download the code and also the images, and then we can start coding straight away.
If not, it should be in a notification. I send a notification this afternoon.
But then, thank you very much, and see you in 10 minutes.
So for the second part of this evening, it's my pleasure to introduce Peter Schneider and David Haber. They work, or Peter is the founder, and David is a lead engineer. They work for a company called Soma Analytics, which tackles, from my perspective, a very interesting problem of reducing stress in companies with a data approach. And they do the practical session now. Very fun. Thank you.
All right, thank you very much again from my side for coming. And how we thought about going through the practical session would be to first start just like a quick heads up on what we're going to see later in code. Then go to the coding, and after we've seen the coding, we will go and see what are little tweaks that we could do in order to improve our results or to improve performance. And in the end, we will see some already pre-built frameworks that you can use to solve certain problems that occur with restricted Boltzmann machines, because I mean, for most of the software, you don't have to write it from scratch. And I will do the first part. They will go through the practical session, and then I will conclude. So what we're going to build now is basically, you've seen this already, it's a restricted Boltzmann machine. And what we're going to use as a data set is the MNIST data set. I guess most of you are familiar with this, but for those who are not familiar with this, It's basically a data set of handwritten digits collected from shacks in the US. And the simple network structure we're going to see is we'll have 784 input units that are binary, so they only take state 0 or 1. And we will have 250 hidden units, which also only take states 0 or 1. And a single unit, so because you need later the formulas to implement them. A single unit will be activated by these kind of functions. So we have the sigmoid function. This is basically this function. Okay. And the x, so the input to the sigmoid function is this sum, or later we will work with this in the matrix form. So for the upper part, we have wx plus c, which is the bias, and I mean, it's quite straightforward. For the lower part, we'll have wh plus b, which is also the bias. Yeah. And each unit has then, in the end, we have a probability which informs us whether this unit is on or not. Okay? So this is now what we built. Then the quick refresher on the gradient. So what we want to find in the end is the maximum likelihood. So we want to find parameters for a distribution that the data has most likely come out. This is our goal. So, and we have this very nice likelihood function. The big problem we have is we cannot solve it analytically. So we have to find some way on how to approximate this gradient. And this is what Kristen has already introduced. This is, in the end, the contrastive divergence algorithm. And what we want to do is, we want to find samples for the visible units. And these samples can be drawn via Gibbs sampling. And then in the end, give us a chance to estimate this probability and finally update parameters. Are there any questions so far? Because I mean, getting this is really important to be able then in the end to implement it. You'll see it's very straightforward. It's very complicated here, but it's very straightforward. And sorry. This is basically what you've seen here now. Here we sample data. Okay, we start with some observed data, so V0. This is data we actually have, so this is our MNIST image. And then we start Gibbs sampling. So we plug in the visible data, sample a hidden probability, and then get a hidden sample, which is then in the end binary, right? By just comparing it from with a number drawn from a uniform distribution. Okay? Is that step clear? Okay? And then we should do the same. We have now an update on the hidden unit. And now we can use this update and sample, get a sample for the visible unit, right? By plugging in this sample we already have. And then we get another updated sample of the visible unit. Okay, and we can do this for k steps. In our case, we will only do this for one step, because in the practice field it's shown that's enough. Okay, and these samples, okay, we have a hidden sample, we have a visible sample after k steps. We can use these samples to compute now or update for the gradients, right? Because in the end, the gradients lead the way to a maximized likelihood. And we can basically plug this in, right? We can compute the probability for a certain hidden unit being on. We have this, and we can do the same here with the already given data. And then we have the update. And over time, we should see some convergence in the error to lower convergences, which in the end is then an increased maximum likelihood. Well, an increased likelihood. And hopefully, well, in the end, a maximum likelihood. And now I guess David's gonna turn this into Python code. And yeah, let's start.
Let's do this. So who wants to implement an RBM now? Who can already implement an RBM? Oh, okay. Let's look at it. Perfect. So the idea is, so I've often found myself go to meetups and actually walk away afterwards and I don't know what to do. So the idea is now that we've talked a bit about the theory and looked at some of the methods behind RBMs, and now we actually produce some code that hopefully works in the end. Depends on how good of a job I do. And then you actually can walk away with some piece of code that you hopefully serves as a basis for further implementation, and you can extend it with some more fancy methods. I will walk you through, hopefully everyone who wants to implement the RBM has downloaded this code, and the link is on the Meetup page. Also, it's useful if you have Anaconda installed, if you actually want to run it. And also, some form of a text editor. We recommended Sublime text editor. Obviously, you can use some other editor of your choice. So, we've provided the rbm.py in the zip file. And I will walk you through the first part. My goal is to make this crystal clear that you find RBMs very easy at the end. What we do, first of all, we have, as Peter mentioned, 784 visible units. This is where we feed the data in. 784 because I think there's 24 by 24? 28 by 28, my math is really bad. And we have 250 hidden units. This is the structure of our network. So we can envision we have 784 units at the bottom and 250 at the top. Now, we want to do 500 training epochs. This means we look at the data set during the training. Again, we do a form of unsupervised training here. So what we do is we pretty much feed in the MNIST data set, the digits that we've seen previously. And we want to run over the whole data set 500 times, okay? With a batch size of 50. So what we do is we concatenate, Christian mentioned this before, we concatenate different samples, different images. We use 50 at a time to speed up learning and also get a better accuracy. A learning rate of 0.1. So every time we adjust the weights, so we have the visible units, the hidden units, and we have the weights in between. Every time we adjust the weights, we can define how much we want to adjust them by the learning rate. And we also heard about the momentum and the decay, which we set to 0.5 and 0.0002 here. Okay, that was the boring stuff. So what we do now is we initialize some variables, the weights, we initialize the hidden biases, the visible biases, and pretty much what we use here is just some NumPy data structures to hold all the data. And then some more, let's call them auxiliary variables that help during training. So this is where it gets exciting. Obtain data set. What we do is we have some helper file, some helper methods implemented already. I think Google has provided some sample code that we've adapted for this purpose. And we ask for the MNIST data set. It puts everything that we need in shape, puts it into the respective data structures, and we can use it for training. Look at if you're interested, it's very convenient also for your own experiments. So look at the input_data.py, and you can use it for your own experiments. That's very good. Okay, we do some more here. We have set up the plotting. At the top, you might have seen that. Have we removed that? The matplotlib? Oh, sorry, that's in the plotting, right? Perfect. So if you go to plotting.py, we have created some plots here that you can use. At the top, on some architectures, depending on what you use, the plot might not appear. It's almost impossible to cater for all different configurations on a computer. So if you find that your plot is not appearing for some reason, you might as well try to remove the line 2 up there, or try any of the other backends that you find on the matplotlib website, and just try out, hopefully one of them works.
I can also assist you if there's some questions.
And just a further comment on the script, so we've tried to keep the rbm.py sort of standalone, so we wanted to make it very easy to implement, so that's why we created the plotting.py, which is then something separate that you can use. Perfect, so we set up the plotting here, we will see that later, and this is now where we actually start. So what do? We said we want to do this 500 times, okay, we want to run over the data set 500 times, and we work in mini batches. So every time we look at a part of the data set, we draw 50 samples, and then we do the training over the 50 samples. Any questions so far? We haven't actually started training yet, so this is all preparation for the exciting part. Perfect. Again, this is why it's so helpful. Working out mini batches is often the first pain. So you just call next batch here and you get 50 samples through that input underscore data. So what do? We heard about the contrastive divergence algorithm. We will pretty much implement that now. For those of you that are keen to sort of think about this a bit more, we will implement the first step, the Gibbs step first, and then you have, let's say, 3 to 5 minutes to think about the second step. So we have to push the data up, we have to push it back down, and then we complete the implementation together and make it work. So what do? First step. We have the batch, we feed it into the visible nodes, okay? And what we do is we actually calculate the hidden, we have to compute the values for the hidden nodes. And first what we do is we apply a simple transformation, okay? So what we do is we multiply our data with the weights that we have, okay? The weights are the ones that we want to adjust. And what we do is we just add the biases. By the way, if I make any mistakes, please correct me. Okay? So this is the very simple, I think we have it on here. First transformation, so we do WX plus the hidden biases. So far, so good. So we have calculated the input to the hidden nodes. Now what we want to do, we want to calculate the probability. So we heard that we have a probabilistic model. So what we do is we actually transform our input into probabilities. And what we do, how we do that, we also call this the activation of the units. And we take the input and then apply the sigmoid function, which we also defined in one of the utils files, to actually get the hidden activation. Now, interesting step is what we do is we actually have to calculate the states of these hidden units. So we've calculated the probability that one of these states is turned on. And now what we do is we sample the hidden states from a uniform distribution to actually get some sort of information which units are actually turned on and which ones are turned off. So what we do is we take our hidden probabilities that we've just computed. Okay, so this is in line 93 where we've computed them. Line 94, we now say which are the ones that are actually larger than random numbers from a random distribution. Okay, and I give the size, so I say this should obviously have the same size as the NumPy array that I've defined in 93. And this will be 50 by 250. Why is that? Because we have 50 elements, 50 elements in our batch, and 250 hidden nodes in our RBM. Okay, so what have we done so far? By the way, if there are any questions, please, this is not a one-man show, so you're encouraged to ask questions. What we've done so far, we've taken the data input and we've pushed it up the network, and now we have the hidden nodes where we've calculated the activation and now sampled states from that activation. So the hidden nodes will have values either 0 or 1. Any questions? Perfect. What we now have to do is we actually have to push the data back down, right? Any volunteers, any idea of how this works? It's very similar to 92 and 94, but we just do it the other way around.
the solution, but I have a question.
Yes.
Not clear in my head, but would it make a difference if you only sample at the very end?
What do you mean by the very end?
Well,
After you've pushed the data back down?
uh,
Yeah, so really good question, by the way. The idea is that you are trying to achieve, so the hidden units are a form of a bottleneck, right? We want to encode a compressed information, right? So they have to be either 0 or 1. And what's commonly done is that we put a limitation on these hidden nodes and say they can only hold 1 bit of information, okay? So they can be either turned on or turned off. Now, if we don't sample, what we do is we use the actual real values and push them back down. Okay? What we will do in a second is we will take the hidden states, so the values that we've sampled, either zeros or ones. Okay? And by that we use the states. If we don't do that, we use the real values and actually use the real values to calculate the reconstruction when we push this down. And they've actually shown in there's a paper by Hinton, I think, which is it's called a Pragmatic Guide to Training, a practical tutorial on training RBMs. And this is actually where they discuss this issue, whether they should use probabilities or states when going back down. And the idea is if you can't, or if you don't enforce this limitation of the 1-bit information bottleneck, training becomes very unstable. But it's a great question, and there's a good discussion in this paper actually on this particular topic.
It's just it's like you introduce extra noise if you convert to states instead of doing this. But actually, I think for fine tuning, often the real values are propagated. Then you don't have.
Yeah. I guess depends on on the architecture you use for fine tuning, but for sure, yeah. Perfect, great question. So what we do now is push the data back down, okay? And what we do is we say, let's calculate the value that comes back to the visible units, okay? So what we do is we do the exact same thing actually, just that we take the states. So this goes back to your question. We could now obviously take the probabilities to avoid the noise and keep that 1-bit information criterion. We take the states and actually multiply that with the weight matrix to get back. So we have bidirectional connections, as we mentioned before, between the visible and the hidden states. And what we do here now, question, which biases do we use?
Visible bias.
Visible bias. Perfect. What is the next step? Exactly. We have to calculate the visible activations. So what we do is we apply the sigmoid function to our visible input. So the input that we've given back to the visible nodes, and we apply the sigmoid function to get real values again. And what we've done now is we've done the 1-step contrastive divergence. Okay, if you remember the contrastive, we actually want to. Is this visible for people here? Yeah? No? Yes? No? No? Anyways, just envision, I'm sure you remember the algorithm, contrastive divergence. What we do is we go up and down pretty much k times, okay? And in experiments, they've shown that, and as Christian mentioned earlier, it is enough in practical experiments to actually just use 1 step, which is quite interesting. It speeds up training a lot. And what we've done so far, and you can also look at the slides later, I believe we'll upload them somehow. We've gone up once, and now we're going back down, okay? Some of you might think, oh, this is so trivial now after all this math, but that's actually what it is, right? One of the possible extensions for this is if you are interested in sort of taking this forward, you can take this and actually put a for loop around this, do slight modifications to the code, and then you can get the real CDK algorithm where you can define the K and do this multiple steps and actually compare how the result differs if you make the K larger. So, long story short, we've gone up, we've gone down, CDK is done. Okay? What we need to do is we need to go up one more time because one of the terms in the update rule that we will implement in a second depends on the hidden probabilities given the data that we've obtained after K steps. You might remember there was like a VK in the algorithm. This is what we have there. So we have the V1. V0 is the data we feed in initially. V1 is the data after one step. And this is what we need to calculate the hidden probabilities once more. So what we do is, exact same thing. We do the np dot. Yep.
So what if the sample the states here?
Sorry?
So what if the sample now?
Good question. So, same paper, there's a discussion on why we use states here and why we do not use states here. And actually they have shown, I think Peter, you also have an explanation about this, but they've shown that you actually don't need to sample here and you get very good training results without sampling here and using the real values. What we do is we need to calculate the hidden probabilities based on the CDK sample that we've obtained. What we do here is now, just like before, we get the data and actually multiply it with the weights, and then what we do is we add the hidden bias. So we do the same thing again. All right, and here now. This should be pretty straightforward by now. So what we do is we get the sigmoid function again, applied to the input that we get. And now we have the hidden probabilities given the sample we've obtained after K steps. And this is pretty much now what we needed to compute. There are a few more, for those that can see it, maybe it also makes sense maybe to move a bit to the back or to the front, depending on where you are. So what we will do now is we will implement 7, 8, 9, and 10. Okay, 7, 8, 9, 10 lines on this algorithm. I can actually also show it here for a second. So we are all on the same page. So what we've done so far is we've initialized the V0 to our data. Okay, we have done this step once because we're implementing CD1. So we sample up, then we go down. This actually recommends that you should also sample. Again, you don't have to do that, but it's also a good point for experimentation to actually try both. And what we do here is now we calculate the deltas. So this is pretty much where we do the real work. And given the probabilities and samples we've obtained, we will now change our weights in the direction to make progress in training. What we need to do as a last step before we can calculate the deltas, we will need this term. So it's the hidden probability, the probability that a hidden unit is turned on, given the sample after K steps. This is where we have to sample up this weird second time, times the data, the sample that we've obtained, and then times this, and we also need to get these terms. And this, again, this looks very difficult, but it's pretty straightforward in code. So what we do is, by the way, if this is too fast, I will also leave it on there afterwards so you can copy it, or we will also provide a solution.
So like I had the way you write it here in NumPy, this was the vectorized implementation slide.
Exactly.
So there you have exactly, basically, given the dimensions of all the variables that go in, and then it's merely a translation to the NumPy functions.
I believe we will upload the slides or put them in the comment section so you can access it afterwards. So let's calculate a few more terms. Line 96 on this editor now, where my cursor is. What we have to do is we have to calculate this little term, these little terms here. This is what I'm doing right now. So what do we do here? We actually calculate the data that we have. So this is the V0. Okay, V0 is the raw data that we have. And we times it by the hidden probabilities. So this is V0, probability given V0 times the data. Okay. And what we also need to do is, and I call this nec prots, we need to do the same thing. But this time, we don't use the original data, but we use the VK samples that we've obtained, or the VK activation probabilities that we have obtained. And we will actually multiply this with the hidden probabilities. So this is now the second term, which we have here. Okay, what we're doing now is we're pretty much just putting this together so that in a second we can write the update rule and then do the actual training. We need to do two more for the biases. Again, there is two terms in the biases, in the bias delta rules at the bottom. So what we do is we name the variables in a way that if you follow papers, it should be pretty clear what this actually means. And what we do here is we take the sum of the hidden probabilities in the second phase. So this is when we sample back up, and we also take the sum of the data that we've obtained. Now, if we apply, for those of you that have used NumPy before, what happens now if you just write it like this, you get a single number back, right? So what we have to do is we have to say, please take the sum over axes 0 in this case. Okay, so it collapses one of the axes only, and we get 250 values back. And then for the visible activation, we do the same thing, and we should get 784 values back. So now we're doing the real work. And this is literally just applying the rules that we have here. So we take one term, subtract another, and then do these easy calculations at the bottom. What we do here is we take the positive, as we call them, the positive product. So this is this term positive because there's a plus. It's called the positive phase sometimes. Okay, so we have the pH1 given V0 times V0, and now we take do the subtraction, negative brots. Now there's something that's not in the algorithm here, and because you use batch training, what we now have to do is, because we have a sum here over multiple data points, what we have to do is we have to average, and we do the divided by the batch size. This increases training quite significantly instead of doing, as we said, one training sample after the other. And what we do here is, I've actually forgotten one term, right?
I think the positive negative refers to the propagation direction.
Exactly.
Because you can as well formulate the whole thing as stochastic gradient descent, where you don't maximize the likelihood, but minimize the negative likelihood. And that all sounds pretty logical.
So what we're doing here is we are building a sum over the data and also the hidden probabilities. No one has noticed this. I thought someone would tell me. And we need this, if you check the update rules, this is exactly what we need to update the biases. All right. So we've done the weights delta, which was no problem, and now we do the visible bias data at delta. Okay. So what we need to do is we need to compute the term that we have, the two terms that we have in line 9 and 10. Okay. So what we do is now we have all the ones, and we also need to divide by the batch size, because again we do batch training. And then the same for the hidden biases, divided by the batch size. And now we are in a great position, because we've computed all these different terms, and now we actually do the adjustment on the weights before we go to the next iteration in training. And this is where everything comes together. So we said we have the learning rate, which determines how big the step at each iteration is. Okay? So we times the weights delta by the learning rate. We do the same for the visible biases and for the hidden biases. And now, there were two other points mentioned which we haven't included, which greatly improve, again, a great point for experimentation. So try to change all of these parameters, and also try to work with weight decay and momentum, which is what we will implement now. So weight decay, again, it's good if your weights are fairly small. So we have a term that we add to this update rule, so that weights will stay small over time. Okay, there are also great discussions in the same paper actually. So what we do is we subtract the term from our update to make sure if you subtract something it becomes smaller. And then to at the same time increase the training progress, okay, we actually, and I believe this also gives some stability to the training process, we take, I'll move this over, we take the weights from the previous iteration that we had. So you see down here that we actually store our delta in a helper variable, so we can use it the next iteration. Okay, and so what we do is we have the learning rate times the weights delta minus the decay term plus the momentum term, which relies on the previous delta, which means the one that we calculated at the previous iteration. And interestingly, it's often suggested that you only add the momentum to the weights, to the biases, because obviously here we have a weight term. For the weights, it doesn't make sense to add or subtract something that contains the weights to the biases. And what we do here, we add the momentum the same way as we did it for the weights in this line. Oh, this is the only annoying thing about Sublime, is something that comes up and makes you want to purchase it. We can just press cancel. Great. So we've just implemented around 40 to 50 lines of code. Let's see if it actually works. Oh, there's something missing. So we need to do that too. Often, I mean, those of you that are familiar with machine learning, we need to get some intuition for how accurate our model is, whatever that means. Okay, so we want to calculate some form of error over the training set, and also over something that, who's familiar with the idea of a validation set? Oh, awesome. So what we do is we use mean squared error. There are also great discussions about whether this is the best best measure to actually use. And what we do is we calculate the reconstruction error over or between the data that we feed in and the data that we sample from this particular model. And then what we do down here, we've already prepared that, so we want to have some progress reporting and then some plotting at the bottom. So let's actually try to run this. It's a moment of truth. Oh, line 107. Probably from neck prods, neck data. Can anyone spot the mistake? Neck prods. Wow, that's actually very simple.
Yeah.
That should do the job. That looks better, huh? So let's actually see if it works first, and then we look at the individual figures. So the reason why we are providing these figures is because it's always great to get some idea of how your model works if it actually learns. And, oh, that looks good. Perfect. So it seems to work. Let's actually see if it learns something, or if it just does some random stuff. We obviously expect the training error to go down. It often also fluctuates very much in the first iterations before it finally drops down. Do you want to talk about these figures, Peter, or? Huh? So we've prepared a few ones here. I mean, these are like standard figures that you look at, but I think they're a great start if you want to experiment with these models. So we have the training error and the validation error here. What we do in this plot, we have reconstruction plots. So now this is over validation data. Okay, so we are showing how the model reconstructs validation data that it hasn't seen during training. Looks pretty bad still. And then what we have here is the receptive fields. This is something that Christian talked about. It's pretty much a representation of the weights between visible and hidden units. Okay, we expect these to show interesting patterns after a while. And what we see here is hidden unit activation over batch. This is also often interesting. So we have some form of probability here. As the color. On the horizontal axis, we have the 250 hidden units. And then on the vertical axis, we have 50 data samples that make up our batch. And obviously, if most of this, or actually if all of this is black, it will tell us that the hidden units are always turned off. If it's white, it would mean they're always turned on. And we are ideally looking for something that's in between. Okay, but obviously, if you experiment with sparsity, this is where sort of one of the most interesting plots then, because you try to have some form of regularization in there, where you sort of penalize units to be turned on during training. You have a question?
You have an idea what happens around the hidden unit 130? There seems a white line there.
Yeah, interesting. Seems to be always on.
Yeah.
Not sure.
Perhaps it's somewhere at the border of the.
I mean, let's see how far we are.
Representations.
Yeah, let's actually see how far we are into the training. 10. So what we can see is that the training error, this is one thing, has gone down quite drastically. That's good. Let's see, I'm waiting for a bit because I want to see if it actually disappears. Reconstructions have become a lot better. So initially we had the weird 9, that looked quite bad. And here we have the receptive fields. So again, depending on sort of how many hidden units you use, these will look quite different. This is something that they always motivate with the visual cortex. So they say this is if you try to see how these machine learning models relate to how our human brain works. This is one of the motivating examples they always use, that they try to, these receptor fields show feature detectors that are similar to how the V1 or one of the lower areas in our visual cortex work. For the neuroscientists among you, this might be not as accurate, but at least I understand that they always use that. And let's look at the hidden unit activation. This line still seems to be here. Honestly, I don't know why.
This is the center, which is most often white.
Yeah.
They don't have any local thing to them, the hidden units, do they?
What do you mean by local thing?
Do they translate to the original 784?
So
It's
you're
a
showing us
compression.
20 receptor fields to the left. How do you pick them? We can't see the receptor field of this one, can we?
Perfect, exactly. So we actually talk about two plots here. You're talking about this one, and you're asking about this one.
Well,
You're
they should connect, right?
exactly. You're absolutely right. So for this example now, we've chosen 20 random ones. But obviously, you want to have these aligned in a real experiment that you can actually see. So the first thing you would do is you would now look at actually this batch and see if this, what happens to this line. You would probably use, so for this training, we are always showing, this is always based on the same data. You would obviously vary that a bit and look at other batches. The same for the
to disappear already, it's hard to recognize.
Yeah, maybe it's a question of just letting it train for a while. But you're absolutely right. I mean, this is by no means sort of extensive. So we will obviously want to align these different plots. This will make experimentation a lot easier.
I've got another question actually.
Yeah.
Can you remind me how we initialized our weight vectors
Yep.
at the beginning? Was it all 0?
So the weight vectors, let me find the line, is here.
Or is it random?
Line 40, so we use very small random values. Again, this is what's sort of the recommendation in literature.
Mm-hmm.
And actually, I think we've done quite some work on this. And we found that if you have all zeros, then your training gets a lot worse. Also, this has a lot to do with like numerical instability. And this seems to work pretty well. Obviously, you can fine-tune that as well as all the other parameters.
But it's close to 0 compared to the weights we'll have at the end of the training.
Yes.
Okay. Mm-hmm.
So one plot, the next plot that we actually thought of building was a histogram of your weights to actually see how they behave over time. And again, you expect that the weights get slightly larger over time, but if they get too large, this whole thing pretty much blows up, and the training becomes pretty unstable. That's where sort of regularization techniques come into play, and you look at more sophisticated techniques. Let's look at the plots one more time.
Excuse me, could you show line 96 for just a quick second?
Yeah, sure, no problem. Again, we will. Oh, actually, now I can. So we also have the RBM_final, which holds everything we've implemented. So you can just look at that. You can just look at that, and you should find everything in there. We didn't want to say it first because then people usually don't do anything. But yeah, RBM final holds the working version of what we just implemented, and you should find everything in there.
So the
Yeah.
first version of your plots, they all looked the same. Do you remember?
Those ones.
Yeah, those ones, and also the hidden unit activation of a batch was also pretty much the same.
Mm-hmm.
Is this due to the mostly 0 weights?
Yeah, initialization.
It's basically when you draw the numbers from a standard normal distribution. Yeah, so mean 0 and deviation 1.
Yeah. So, yeah, I was wondering whether the weights at the beginning were really small compared to what they were at the end.
Yeah, they probably are.
Yeah.
Yeah.
So that's
Yeah. Perfect. I mean, I would say we just move on. If there are any more questions about the code, about what we've done, what my hope would be is that you use this as sort of or as a foundation for experimentation. So this is some code that works. It seems like it does some training, which is great. So you can extend this, and Peter will talk about some of the possibilities of how to actually implement this, and sort of get from this experimental demonstration code to something that you could potentially use for more interesting examples.
Okay, so potential improvements and extensions. So I mean, you've seen now this is a NumPy implementation, so everything runs on the CPU. And first problem you have probably seen already, it takes quite a long time to run one epoch. So depending on your machine, it may take like 40 seconds, 60 seconds if you have an older computer. But this is not really fast, and especially if you have larger images, which would only have 184 pixels, but much more. This takes forever. So an observation we can easily do is, a lot of our stuff that we're doing is basically matrix computation. And the GPU offers a great way to do this highly parallelized. So we just basically put the entire matrix on the GPU and do our computations there. One thing you always have to do, reminders, so copying data from and to the GPU is usually the most expensive operation, or one of the most expensive operations. So you should really also optimize on the batch size when you work with this. Then the second problem is that, so we've used now a simple sampling algorithm, but later when the weights get bigger, the sampling rate, the mixing rate goes slower. So contrastive divergence introduces a bias into our gradient estimate. And the longer it takes for the sampling to converge to its stationary distribution, the more biased our estimates are, because we have we only take one Gibbs step. Okay, so the longer the time is, the more bias we have. So and there are alternative sampling schemes to converge quicker to our stationary distribution where we actually want to sample from. And so there's just as a hint is parallel tempering and adaptive parallel tempering. These are two common methods to be used to improve this the mixing rates. Second point is where you can also continue to improve your restricted Boltzmann machines once you've started building it. It's using a sparsity constraint. So the basic idea is, when is a binary unit more discriminative? So what we've seen already in the plot, if it's always on, it doesn't contain any information, right? So the lower the probability of a certain unit to be on, given a certain sample, the more we can increase the discriminative power or performance. I mean, we also don't want to get it to 0, so then it never turns on. But a lower probability should be better.
Do you force the unit activation states to be sparse, or the weights? Or
sorry,
or we can discuss this later.
And then the last point is we can use different layer types. So because I mean you do not necessarily always have binary input data, so you could use Gaussian data or rectified linear units and to model multinomial data. And these are some improvements you can use for the individual RBM. And then, I mean, in the end, it's just stacking the RBMs to a bigger network and use this network for either as an initialization for your neural network or in any other way. And then this is just for yourself a list of frameworks. It's not complete. And but for example, for the GPU computing, TensorFlow has come out, so you can use this one. And what's very common, but kind of harder to use, is Theano. NumberPro is another way, but this is commercial. And you could use CUDA together with PyCUDA, which is a very tedious way on writing CUDA code on if you want to use Python. And then we have RBM frameworks. So Pylon 2 was one of the most famous frameworks when especially the RBM topic came up and was like getting some some attention. And then there are other frameworks like blocks, Caffe, Lasagne, Torch. I mean, you also use this.
Coffee.
Yeah, you use Caffe, right?
Yeah.
It's a lot of food. And that's basically it. So if there are any other questions.
Did you try TensorFlow?
Sorry?
Did you try TensorFlow?
Yeah, I tried it out, but so for parts of it are not yet implemented in TensorFlow. So you can do not use it straight out of the box, so you would have to write, especially the contrastive divergence yourself. Yeah, but that's it so far. So are there any questions? Then I think we've come to an end. If you have any further questions or are interested in a discussion about machine learning, we're happy to stay in contact with you guys, email addresses, and then thank you very much. You had a question or?
Thanks.
Okay.
Thank you.
Thank you very much.
So thanks also on behalf of the Meetup group and the ACM chapter. I think first of all to our host TNG, really great work also with the pizza, thanks a lot. To Soma Analytics, the team, to giving the great practical session, and to Christian or Dr. Leibig to doing the great theoretical introduction. Thank you, have a Merry Christmas and see you soon.